Let's think about what's happening in our chemical reactions on the molecular scale. So in collision theory, when we're looking at the molecular scale, our reacting molecules have to hit one another. And on average, there's about 1 billion collisions per second. Now, not all those collisions are going to result in products being formed because the collisions have to have enough energy to break the bonds that are holding the reactant molecules together. They have to overcome our activation energy and have enough kinetic energy to form that activated complex. Now, this isn't the whole story. We also have to make sure that our molecules collide in the proper orientation. So the right atoms are hitting each other in order to form new products. These two factors, the orientation factor and the collision frequency, are what make up the frequency factor in our rate constant. So the A that we talked about previously and calculated using the intercept, that is made up of both the orientation factor and the collision frequency. The orientation effect has to do with how the atoms are aligned. They have to be making the collisions in a very specific way in order to have an effective collision to make our products. So let's look at an example where we have NaCl that reacts with itself to form nitrogen monoxide and chlorine. In order to be an effective collision to form the Cl2, the two chlorine atoms need to collide with each other. If our collision happens between a nitrogen and a chlorine, no bond will be made. If our collision happens between two nitrogen atoms, no bond will be made. Only when they collide and form an effective collision will we get our products. Typically, when we write a chemical reaction, we're looking at the reactants that we need and the products that are formed. But there is a larger story going on. There's typically a series of smaller steps that happen in order to make the products. A reaction mechanism helps to write out those smaller steps that happen in order for the overall reaction that we write. Kinetics helps us to determine and understand the sequence of the reactions in that mechanism, those steps that are happening in order for the reactants to eventually form the products. Let's look at an example of a reaction mechanism. Our overall reaction, our reactants are H2 and iodine chloride. The products are hydrogen chloride and iodine. The mechanism in order to achieve this overall reaction actually forms an intermediate, HI, that is produced and then used up. If we look at the overall mechanism, the HI will cancel out, and when we add the reactants on the left side, we get H2 gas plus 2 iodine chloride gives us 2 hydrogen chloride and I2, which is the overall reaction. However, each individual step this shows each individual step that has to occur in order to make the products. These are what we call elementary steps. It can't be broken down into simpler steps for the chemical reaction. Because I2 is made but then consumed, it doesn't show up in our overall reaction. This is what we call an intermediate. It forms but then gets used up. When looking at our elementary steps, if we consider the number of reactant particles that are present, this is what we call the molecularity. And so if it only involves one particle, we call it unimolecular, one particle that produces products in that elementary step. If it involves two particles, they could be the same kind, but two different particles, we call it bimolecular. And if it includes three particles, then it's termolecular. They're pretty rare though. Unimolecular and bimolecular are much more frequent because it is difficult, and the probability of three molecules coming together in the proper orientation with the proper speed is, the probability is pretty small. So they do exist, however, they are pretty rare. The molecularity helps us to determine our overall rate of these individual steps. Each step in the mechanism is like its own little reaction. It has an activation energy, it has a rate constant, and a rate law. So unlike the rate law for the overall reaction, we can look at the reactants and determine the rate law for elementary steps. It depends on the reactants. So for reaction 1, our rate is dependent on H2 and ICl with its own rate constant. Because these are both the reactants, there's only one molecule of each, so it is first order with respect to hydrogen, first order with respect to iodine chloride. When we look at our second elementary step, it has its own rate law as well. And we look at, there are two reactants, one hydrogen iodide, so it's first order for hydrogen iodide, one iodine chloride, so that is also first order. It has its own rate constant as well. And so we can deduce these rate laws from the elementary steps. We could not do this in the overall reaction, but we can for using our mechanism. So let's look at some options that we have and the rate law that is produced by these elementary steps. If it is unimolecular, one atom that falls apart to produce products, our rate is the rate constant times the concentration of that reactant. And it is only, or it has an order, it's to the first order. If we have a bimolecular, where it's the same element that is reacting with itself, then our molecularity is 2, even though it's the same element. Our rate law is the reactant. It's a second order with respect to that reactant because there are 2 of the atoms involved. If it is 2 different reactants, it still has a molecularity of 2, but now our rate is first order with respect to each reactant. And if we get to termolecular, where we have 3, and again these are rare, if they're all 3 the same reactant that are reacting, it's going to be third order with respect to that reactant. If it's 2 of the same and 1 different, then it's going to be second order with respect to the first reactant and first order with respect to the second. And if it's all 3 different, then it's first order with respect to each of the reactants. In most of our chemical reactions, one of these elementary steps in our mechanism is much slower than the other steps. We call this slow step in the mechanism the rate determining step, or RDS. It has the largest activation energy, and so the least amount of molecules make it over our energy barrier to make the products. This determines the rate law for the overall reaction because it is the slowest part of the reaction. You can think about it as if you are taking a trip. The slowest portion of your trip, say if you're going through the mountains or there's road construction, that slowest part is going to determine the overall length of your trip. So let's look at an example. If we know that our first step in our mechanism is the slowest, that rate is going to be the rate that determines the overall rate of our chemical reaction. So notice how the rate of our rate determining step is the rate of the overall chemical reaction. It means that our activation energy is the largest. So in our example, we have the biggest amount of energy that we have to overcome in this first step. And then once our molecules make it over that activation energy, it's pretty easy for them to get to the products. So that second step is much faster. The rate law for the first step is the same as the rate law for our overall reaction because the first step is our rate determining step. See if you can determine the overall reaction, the rate determining step, the rate law, and see if there's any intermediates in the following mechanism. Pause the video while you look at this problem. If we want to determine our overall reaction, we're going to cancel anything that is the same on opposite sides of the arrow. So in this case, we have B's on either side of the arrow. They will cancel, and our overall reaction is going to be 2A plus B2 yields 2AB. Because B is produced in the first reaction and used in the second reaction, B is our intermediate. It does not show up in the overall reaction. The first step is going to be our rate determining step because it is the slow one. Because that's our slow step, it is going to determine our overall rate based on the reactants involved. So our rate is going to equal our rate constant times the concentration of A to the first order and the concentration of B2 to the first order because it is the same as our rate determining step.